All right, good morning. I had a bit of a of a panic attack because I realized test 2 is on Tuesday. Oh my gosh, I have to make it. You guys have to study for it. It caught us all by surprise. So, well, I guess not really. I just picked a date a long time ago. Said that's when I'll have test 2. Anyways, so just a reminder, so test 2, or maybe I should do like I wonder if there's a warning signal. Maybe not. How about I do it in red? I know, I put it down in my calendar and then I forgot about it. So warning, test number 2 is on Tuesday. Okay, it's going to be the same setup as last time. So for practice, definitely review the assignments because I'm pulling questions that are similar and they're in the same format, so they're using the same platform. So I think assignments will be good practice. Will be good practice. Okay, I posted more than one proportions assignment. So assignment 9. Assignment number 9 is posted. It's due November 26th, but so that's just because I didn't want you to have to perfect your grades, right? I'm expecting really high grades on the assignments because you have so many attempts. And so I didn't want you to have to, perfect your grades unless you had time. I'll get to the topics. And so I made it due November 26th, but the material is on the test. Okay, so, but the material will be on test number 2. Okay. So the assignments will be good practice. And I was hoping to cover all of chapter 7, but that was kind of like wishful thinking. So that's not going to happen, but we are going to get into chapter 7 a little bit this week. And so test number 2 will cover chapter 5, 6, and 7.1, 7.2, depending on how far we get, oops, on Friday. Okay. So it's going to focus on chapter 5, 6, and whatever little bit of chapter 7 we get into. Okay, so you don't have to worry about the previous material. That's not going to resurface until the final exam, right? Which is also kind of hot on our heels. Things move quickly towards the end of the term. I know it doesn't feel like it for you guys, but it does. So chapter 5, 6, and 7.1, potentially 7.2, they're basically the same. So usually I just kind of roll them into one, but okay. One thing that I will note is for this test, there will be a long answer question, which you have to submit your work to, and then I'll mark it, okay? I only plan on doing one of those. The other ones will be taken care of with just the test. Okay, so it'll be a timed maybe I'll say this. So test number 2, it's going to be the same as last time. So it's going to be a time test, timed 100 and how many? We have a 60 plus 20, 80-minute class, right? An hour and 20 minutes. 80 minutes test, open from, when do we start? 8 to 9:20 PST. Okay, just like last time, I'll be in the Zoom room if you need me, if you have any questions, right? But you don't have to be here because I trust that you're all adults and you can not cheat on your own. So I will be in the Zoom room. If you have any questions during the test, but you do not need to be there. I guess I should underline the not need. If I just underline need, you might misinterpret. You do not need to be there. Okay, so it's just if you have a question. So the new thing is that you have to submit your work. Okay, so there will be, so what's new is that there will be a long answer question that you have to submit all your written work to. So what that means is that you have to have, paper ready so that you can write down your answers, but also you need to be able to scan your work and upload your work. Okay. And what I want to do is I also want you to jot down the answers to all your questions that you're submitting. So even the short answer questions or any questions, submit. So write down your answer, because that's how, because I remember last test, right? Some of the questions weren't submitting and, oh, I did it, but it didn't submit, blah, blah, blah. So now you have a record of the answers that you would have submitted, and then I'll go back and I can check if there's a question missing, then I can check against that work that you've submitted. Okay, so you need to be able to scan your work. Okay, so there will be a long answer question. Which I will mark separately. Okay. As a, I want to say a ledger, but kind of as a record of all the questions that you've submitted. So write down all the answers you've submitted as well as a record in case the submissions don't go through. That's not what happens, but usually, if you forget to hit submit, then it doesn't submit it, and that just makes a mess. So well, I don't know how many questions there will be, but probably about 20 is, pretty typical. Some of those are really short, right? Some of those are really short, just quick multiple choice answers. And then some of them are a little bit longer, but I haven't made it yet because I had completely forgotten that we have test 2. So I don't know how many questions there will be, but roughly 20, but some of those are really short. Okay. So write down all the answers you've submitted as well as a record of your test. Okay. This way, if a question is missing, so this way, if a question is missing, I can fill it in after the fact using your scanned work. I can fill it in after the test using your scanned work. Okay. So make sure that you're able to scan multiple pages. So if you don't have a scanning app yet, what are you doing? No, you've probably had to scan stuff for other courses already, right? So you probably have a scanning app, I'm assuming, kind of ready to go that you like. I really like Scannable, but there's Cam Scanner and there's Adobe Scan, and most phones have a scanner built in. I'm on an iPhone, and I don't really like the built-in scanner, so I prefer Scannable. But your goal is to figure out how to scan your work, right? So you must be able to scan and upload your work for this test. Yeah. I want it as a PDF because the JPEGs tend to be too large, and then Moodle makes a fuss and whatever. So one PDF. Right, so look into, download a scanner. And what I did is I just downloaded a ton of different free ones, right? I don't want to pay for a scanner. I don't have to. And then I just had a couple of pages, right? So if you're working in a, in a notebook like this, oh, now I'm Struggle City here, but you would just scan a page, scan the next page, scan the next page, and make sure that you're able to upload it as one PDF. Okay, and try out the different ones and figure out which one you like. Okay, so what I'm gonna do is I give you 10 minutes. So you have until 9:30 to submit your scanned work. Okay. You will have an additional 10 minutes to scan and upload your work. To scan and upload your work. Okay, so until 9:30 PST. Okay, and that's a hard stop. Okay, so make sure that you're up and running and you know how to upload, you know how to save it as a PDF, and you know how to, submit it on Moodle, etc. So, but you'll have an additional 10 minutes. Okay, I know that's after class time, but usually you'll be fine. You'll be able to scan and upload within the 9:20 mark, so not to worry. Okay. Good. Let's continue. We started chi-squared tests yesterday, or not yesterday, I guess, Tuesday. Man, time flies. If you think of any questions for the test, then just you can put them in the chat, but I think we've covered most of it here. Okay. So let's say, just as some quick review, right, we introduced a new test statistic, which was the chi-squared test. We introduced a new test statistic chi-squared, right? And we said, just as a note, right, chi is pronounced chi, right? Or if you write it, it's chi, but you don't want to say chi because then you sound like you don't know what you're talking about, right? And I don't want that for you guys. So you say chi, okay? So chi is a Greek letter, and it's just kind of this fancy script X, okay? So the chi-squared test, for more than two proportions. Okay. Okay. So we looked at, okay, so the null hypothesis, what are some of the things that we need? So there is no, we're not going to do a confidence interval for the chi-squared test. I can't even put my finger on what it would be, but I'm sure there is one. But so the chi-squared test, so a chi-squared test has a null hypothesis that, and it's pretty vague, right? But the null hypothesis in terms of a one-way table, so only one variable with counts. And then today we're going to look at what if I have a two-way table, right? But the idea stays the same, so it doesn't really matter. So the null hypothesis is going to be that there are a couple of different options, but it's in general, it's going to be that the counts that you saw are no different from the expected counts. Okay, and so the observed counts are not significantly different from the expected counts. And we talked about, okay, well, what are the expected counts? That's kind of vague because the expected counts, they're going to depend on some idea that we have about the distribution. Okay, so it's going to be more question specific than this, but in general, that's the chi-squared test. Okay, the chi-squared test statistic itself, so chi-squared is the sum of the observed counts minus the expected counts squared, squared, divided by, oh, not the sum, just the divided by the expected counts. Yeah. We introduced the chi-squared table. Of course, you can use software, but to use a chi-squared table, we need the degrees of freedom, which software would just find. But the degrees of freedom is the number of categories minus 1, right? And that's for a one-way table. What we're going to introduce today is what if we have a two-way table, right? So now I have two variables, and is there a relationship between those two? Right, so this is for one-way tables. The conditions for conducting a chi-squared test are relatively simple, right? We have to have independent counts, right? So the counts in the table have to be independent of each other. As long as we've sampled randomly, then that's satisfied, right? Even if we haven't, we have to say that, okay, well, we assume that these were randomly sampled. Okay, and so and the second condition that we can check, and it'll always check out, is we have to have at least 5 expected counts in each cell. Okay. So the conditions for a chi-squared test are independence, if the sample is randomly selected, this is satisfied. And the expected count in each cell has to be more than 5. Okay, so at least 5 expected counts in each cell. Because otherwise we're trying to detect something that's really, really hard to detect. And so we want to make sure that we're able to detect something. Okay, good. So once we have checked the conditions, then we can go ahead and we can do the test. And I think that's where we left off. So continuing from last day, where did we get to? Oh yeah. And maybe I'll bump this down here. Whee. Fresh page, fresh take. Okay, let me just grab the rest here. Okay. There. Okay. So you've hopefully worked through this example on your own. So we will kind of go through it a little bit quicker, but just as a refresher, right, the teacher had some predicted percentages of his students that would use an online copy of the textbook, a hard copy, or print off the online copy. Right, and so we have these predictions of 60%, 25%, and 15%. And what we first assume is that that's what was happening, right? Until we have proof that no, our data suggests otherwise, right? And so then we would say that the predictions were inaccurate, right? And so it's going to be really question specific, these null and alternative hypotheses, right? But the general idea is that the null hypothesis says that the observed counts are not significantly different from the expected counts, right? Whatever those expectations are. Okay. So the question here only asks for the expected values, right? How many students did the professor expect to buy the textbook, buy the book, print the book, or read the book online? And so, but I think it's handy to set up the table. Okay. So we started with the first expected value. Okay, so what you do is you have 126 students, and we have these observed counts, right? And maybe what I'll do is I'll move this up here because I want to boop, boop, boop. I want to keep going with this table here. Okay. But just as a note, in our expected values, we're allowed to have decimals. We're allowed to expect a portion of a count. That's allowed. Okay, so you don't want to be rounding or anything like that. So here, these are our observed counts, and we have a total of 126 students. So if I told you that, okay, I expect 25% of 126 students to print the online book off, right? And so then how would I find that? Well, I would take 126 times 0.25, right? And so I get 126 times 0.25 is 31.5. And that's 126 times 0.25. And then 126 times 0.15 for the online. 126 times 0.15, 18.9. You just want to double check, right? Because these expected counts should total to 126. If they don't, you did something wrong, right? And so they should total to the same count, okay? So if we take 75.6 plus 31.5 plus 18.9, I get 126, whoops, which is good. Okay. So what I want to do is, the reason I've set this table up like this is because our calculation is going to require taking the observed minus the expected and then squaring it, and then and then squaring it and then dividing by the expected. So from here I can build onto this table and I can calculate the chi-squared test statistic. For now, it just wants the expected values. So we'll kind of leave it there, but of course it's going to walk us through the steps. So it says this is an appropriate setting for a chi-squared test. Okay, that's a fact. List the conditions required for a test and verify they are satisfied. Okay, so the conditions, the chi-squared conditions here. First one is independence, right? So we have to be able to assume that either the sample was randomly selected and that would be, enough. In this case, right, I don't think it says, I think he samples all of his students. Okay. So what we need to argue is that, okay, there's no reason to think that this group of students is any different from a general group of students, right? And so that's reasonable to assume, right? This group is, we have no reason to think that it would be significantly different from a different group of students, right? And so that's what gives us the independence. I know some of you might say, oh, well, how can we assume that? We can't assume they're independent. Well, we have to assume it because otherwise we can't do the test, right? And so your goal is always to argue, okay, here's a reason why we can argue that they're independent, take it or leave it. So the conditions, the first condition is the independence. Okay. And the sample is not randomly selected, but right, there's no reason to think that this group of students is different in any way from another group of students, right? So they would be independent of another group of students. So independence, the sample was not randomly selected, but we assume that this group of students is independent of any other group of students. we assume this group of students is independent of other groups of students. Okay. The second condition is the sample size condition, right? And so the sample size condition is that we have at least 5 expected counts in each cell, right? And so we have 75.6, 31.5, and 18.9. They're all greater than 5. And so we just say we have at least 5 expected counts in each cell. We have at least 5 expected counts in each cell. Okay, good. So next step, we have to calculate the chi-squared statistic. We also have to find the degrees of freedom and the p-value. I mean, if it just wanted the p-value, you would have to find the chi-squared test statistic and you would have to find the degrees of freedom before you can find the p-value. So you would have had to do that anyways. So sometimes it's not explicit like that, but in this case, we're being walked through what to do here. So part D, got a page break there, is find the chi-squared, the degrees of freedom, and the p-value. Notice in the chi-squared case, there is only one tail. And so it's always just, it's a 2-sided test, but we have a 1 tail. So it's a little bit different. So we don't differentiate between the 1-sided p-value and the 2-sided p-value anymore, because we just have 1 p-value. We only have 1 tail. So it's a little bit different, but it simplifies things, right? And so the chi-squared is the sum of the observed minus the expected squared divided by the expected. Okay. And so we can build this out using the table that we started with. We can build this out using our table of observed and expected counts. Okay. As long as we do it in the right order, we're going to be safe. So I'm going to bring it down here, paste, and I'm going to get rid of some of this stuff here. Nice. Okay. And maybe what I'll do is I'll just so it's not so busy. How about that? Okay. Because then what I'm going to do is now I can make a new row with the observed minus the expected. Okay. 71 minus 75.6. 71 minus 75.6 puts me at negative 4.6. 30 minus 31.5 puts me at negative 1.5. 25 minus 18.9 puts me at 6.1. Okay. We don't bother with the totals anymore because it totals to 0, but also they're not part of the counts, right? So the totals we just had to be able to find our expected values, but now we put them out of our minds. Okay, so I have found the observed minus the expected portion. So now what you do is you build this out. Okay, so you want to find the observed minus the expected squared. Okay, so I'll do that in dark green. The observed minus the expected squared. Now, usually when I have this value on my screen in my calculator, I would just square it and then jot down that number right away, right? So you don't have to go back and forth. You can just do each column individually. But, and since I have 6.1 on my screen, I'll just square it here. 37.21. Make sure you put your negatives in brackets before you square them. Squaring a negative always makes a positive, right? So if you get a negative value, then you forgot the brackets. You can drop the negative, but if you want to be sure, you should put it in brackets. 2.25. So I'm just squaring each of these values. Negative 4.6 to the power of 2. I get 21.16. Okay. So now I have the observed minus the expected squared portion, but for each of these, before I add them up, I have to divide these squared values by the expected value. Okay, and so here, let's see if I can find a different color. Orange. Aren't you glad? I didn't say banana. Mm. 21.16 divided by 75.6. Oops. 0.27989. Okay. I'm going to store that. So you want to have, you want to keep as many decimal places as you can. Keep as many decimal places as you can. Right. Try using a store function in your calculator. It keeps going, right? So, but I want to have enough room to do this, the next line. But I'm going to store it in A. And 2.25 divided by 31.5 is roughly 0.071428.6, rounding a little bit, but I'm going to store it. So I'm storing all my values, all my decimals in B. And then if I take 37.21 divided by 18.9, and hopefully you guys will stop me if I slip up on my calculator here, 1.968783069, which I will store in C. So now I want the sum of all of these, right? So the summation is actually on the outside of everything here. Maybe I'll clarify that there. Okay, so now I want to add up all those values. Okay, so the chi-squared is 0.27989 plus 0.0714286 plus 1.968783069 . Okay. So the chi-squared is going to be plus recall A plus recall B. I get is approximately 2.32010582. Okay, so a little bit of work, but once you figure out, you know, the flow of things, I find that it's helpful to set up the table like this, because then you can kind of work through each step of the summation until you have the values that you want to add up. Now you could lay it out just as a calculation in a huge formula if you want. It really doesn't matter. Okay? So our chi-squared to 2 decimal places, let's say, is 2.32. Okay. So the chi-squared is roughly 2.32, which is to 2 decimal places. So now we have our chi-squared, we have our test statistic. I need to find my degrees of freedom before I can use the table, right? Which helps me find the p-value. Or you can use software, but for us, let's just focus on the table for now. So the degrees of freedom is the number of categories minus 1. Number of categories minus 1, which is, well, we have 1, 2, 3 categories, right? So we have 2 degrees of freedom. Oops. Okay. So finding the p-value, we have to find, we have to use the table, right? And because, so most of the time, right, we're not going to have more than 6 categories. So most of the time we're working with this top portion of the chi-squared table, right? And so let's just bring in, I'll even just go to 3 here, because we're going to be focused on the 2 degrees of freedom. Right, so we have 2 degrees of freedom, which means we're restricted to this one line, right? So everything that happens in the 2 degrees of freedom line, because that's what we found. All right. So then what we do is we try to find our chi-squared value. Okay, and what we said was there were 2 ways that we could do it. Okay, we could say that, well, a default alpha is 0.05, right? And I don't think it said the alpha level, so the default alpha level is 0.05. Okay, so in order to be able to reject H naught, the chi-squared has to be larger than 5.99. Okay, that's one way. But what we're going to be doing is we're actually going to try to place our chi-squared, so the calculated chi-squared of 2.32, we try to place it somewhere along here. Okay, and so what we find is that it's actually to the left of 2.41. Okay, which means the p-value is more than 0.3. That's all we can say. Okay. So we find that 2.32, right, would go here. In terms of, so notice, of course, as we move out further and further out into the tail, then our chi-squared values get larger and larger. And so we find that our chi-squared value, that the chi-squared, and I'll say calculated, is less than 2.41 in the table. So our p-value is larger than 0.3. Okay. just to illustrate what it looks like. And the problem with the chi-squared, so what makes the chi-squared a little bit harder to think about is the shape of the chi-squared varies depending on the degrees of freedom. Okay, so as you increase your degrees of freedom, then you start to see this roughly normal distribution. But in the beginning, you've got this sharp upturn and then a downward slope. So it's like this sharp upturn, and then as you increase the number of categories, right, because that's how you increase the degrees of freedom, then it starts to smooth out, but it's usually just skewed to the right just a little bit, even with huge numbers of categories. And I think in the chi-squared table, they have B is the one with 2 degrees of freedom. Degrees of freedom equals 2. So what happens is our calculated 2.32, oh, I guess it would be halfway, a little less than, or a little more than halfway to 5 here. Maybe I'll use a different color. .5, we had 2.41. Okay, and the area in the tail from 2.41 from the table is 0.3. Okay, so from the table, this area is 0.3. So if we think about our number line here, our chi-squareds, then 2.32 is somewhere to the left of 2.41, of course. And so 2.32, let's put it here, has an area more than, greater than 0.3. Okay, so that's the logic. Okay, the other option is the critical value approach, or using the critical value approach. With an alpha of 0.05, the chi-squared that we calculated has to be larger than 5.99 in order to be able to reject the null hypothesis. Okay, so there's 2 ways, and you just have to pick one that you like. Okay, but at alpha equal to 0.05, the chi-squared critical is 5.99. Okay, so in order to reject H0, our chi-squared must be larger than 5.99, which it isn't, right? And that lines up with our p-value of 0.3, right? Because 0.3, we wouldn't reject H0 because it's too large, right? Okay, good. I'm sure the next question asks us to write a conclusion. Calculate the chi-squared, done. Find the degrees of freedom, done. And the p-value, done. Okay, we found that the p-value is greater than 0.3. Okay, and that's good enough. We don't need more than that. But software would give us a better value, and I think it's 0.313 if we use software, but I don't want to throw that in there as if you're supposed to know where that came from, so don't worry about that. But then in part E, based on the p-value calculated in part D, of course, what's the conclusion, and what does that mean in terms of the question? Okay, so we will remind ourselves of what the null and alternative hypotheses were. Copy. I'll throw them down here just so we have them. And part E is the conclusion. Since our p-value is greater than 0.3, right, it is not less than 0.05, so our assumed alpha level of 0.05. So that means that we do not have enough evidence to reject H naught, right? What does not rejecting H naught mean? Well, it means that the predictions of 60%, 25%, and 15% were relatively accurate, right? There is no significant deviance from that. Okay, so since our p-value is greater than 0.3, it is not less than our assumed alpha level, right? If it's not given, then we assume that it's 0.05, alpha level of 0.05. And I'm gonna need to bump this down a bit. Whee. Which means we do not have enough evidence, means we do not have enough evidence to reject H naught. Okay. So I'll shrink this down. Maybe I'll change the, change the color. To light blue. Shrink it down. So that means that if we don't have enough evidence to reject H naught, then we conclude that the predictions of 60%, 25%, and 15% were accurate, relatively accurate. Therefore, the predictions of 60%, 25%, and 15% were accurate. Right? They weren't exact, but what we're finding is there's no significant difference between what we saw and the 60, 25, 15 split. Okay. Nice. Okay. So what we can do is we can extend this and everything stays the same. It's just we make an extension to a two-way table, right? So what we saw was a one-way table. And so here, that's kind of the end of this example. We have seen a one-way table, which has counts from one variable, okay? But we can extend the same chi-squared to statistic. We can calculate the same chi-squared statistic for a two-way table. Okay. And we can calculate the same chi-squared test statistic for a two-way table. Which is when we have two variables, right? The relationship between two variables. Okay. And so that's when we have variable 1 and variable 2. Both of them are categorical, right? And so we have categories in variable 1 and we have categories in variable 2. Okay. So section 6.4, I'll start it on a fresh page here, is the chi-squared test for independence. Okay. And so a chi-squared test for independence. When we have a two-way table, we will be testing for independence, right? Is variable 1 independent of variable 2? Right? So when we have a two-way table, we conduct a test of independence. We conduct a, maybe I'll say chi-squared test. Chi-squared test of independence. Okay. So again, right, if we have something like this, copy. Wait. Right. So variable 1 has categories, variable 2 has categories, and what we're going to test is, okay, well, does knowing that I'm in category 1 of variable 1, does that influence what category I'm in variable 2? Okay, and so, or the other way around, right? And so our null hypothesis is going to be the two variables are independent of each other. Okay. The two variables are independent of each other. Usually I wouldn't really state the alternative hypothesis. I mean, you do when you're doing the test, but here, all you need to know is what's the null hypothesis, right? Because then the alternative hypothesis is that the two variables are not independent of each other, right? And so that's obvious. The alternative is always going to be the opposite of what the null is. But we'll say it here. The alternative hypothesis is that the two variables are not independent of each other. One key thing that I want to mention here is we actually can't determine the dependency, right? So we can't say that, okay, category 3 of variable 1 affects category 2 of variable 2, right? So we can't get specific like that. Then we would have to do further testing. So here, this is just an overview. Are they independent of each other or not? Okay. Okay, so good. So I feel like there was another thing that I wanted to say before we talked about the actual calculations here. Maybe I'll do a follow-up here. Is variable 1 independent of variable 2? Okay. That's what I wanted to say there. The conditions stay the same. So the conditions for a chi-squared test apply to all chi-squared tests. So we're still going to calculate a chi-squared test statistic, which is the observed minus the expected squared over the expected. But now we have multiple cells, right? And so we need to be able to find the expected count in each cell. Okay. So we still calculate a chi-squared test statistic with the same conditions as before, with the same conditions as before. So the first condition is, of course, independence. Again, are these groups randomly selected? So are the counts independent of each other? Counts are independently selected, right? So randomly selected would make sure of that. And the sample size condition, each cell has at least 5 expected counts, has at least 5 expected counts. Okay. So those conditions stay the same. So that's really nice. And then, so now what we need to talk about is, okay, if I have a two-way table. Now, if you have a 2x2 table, oh yeah, so for chi-squared, it's at least 5 expected counts. Whereas for proportions testing, we had to have at least 10 successes and 10 failures, right? So there's a lot to keep track of here. But yeah, in this case, it's 5. Okay. So if you have a 2x2 table, then you're better off doing just a 2 sample proportion test, right? Which we know how to do, P1 hat minus P2 hat, right? And so that's from earlier. So we're going to have more than 2 categories in at least one of the groups, right? So let's assume that we have, something like variable 1, oops, which has category 1, category 2, and category 3. And variable 2, let's put it up there. It doesn't matter, they're interchangeable. Has category A, category B, and category C. Just so we can keep track, right? A, B, C, 1, 2, 3, right? But each has 3 categories, right? So this is a 3x3 table. Okay. There are going to be counts in each of these cells, right? And so here, let's just draw a little grid here. Okay, so there's going to be counts in each cell. There's also going to be expected counts in each cell. And how we calculate those expected counts is we take this row total, divide it by the total number of observations, right? Because that's what we would expect across the board if the category A does not matter, is independent of B and C, right? For category 1. Okay, and so here you would take your row 1 total, row 2 total, and row 3 total. And then we would have a table total. Okay, so here we call this row I total. Okay, so we have I rows, and I'll extend these there. Okay, and maybe what I'll do is I'll use a different color, or try to use a different color for the table total. Okay. So then we're going to have a column total, column J total. So here we have column 1 total, column 2 total, and column 3 total. Okay. There's going to be an observed 1-1 total, right? And then an expected 1-1, right? So here, this is 1-1, 1-2, 1-3. And then there's going to be 2-1, 2-2, 2-3, 3-1, 3-2, 3-3. Yeah. Where we have the row and column. Okay. So 2-1, 2-2, 2-3, 3-1, 3-2, and 3-3. Okay. The expected count for row I, column J, is the row I total times the column J total. Oops. Oh, can't write at all. Over the table total. Okay. Oh, and I guess I used the colors for a reason. So I'll change this to pink, change this to orange,